All right, so we've been talking about the structure of the atom, and so that's where we're going to pick up from. If you recall, there are two regions. We have the nucleus, where we have protons and neutrons, which means we have all of the positive charge, and of course, that's going to mean almost all of the mass. The second region is the electron cloud. That's going to be most of the volume, and what we're going to be spending a lot of time on electrons here soon. But for right now, it's just the region where an electron can be found. And again, we'll give you some more information when we get to that part. So the next thing we want to look at then is the size of an atom. So we know atoms are very, very small. In fact, we measure them in picometers. And so if we're looking at the metric scale, that's 10 to the negative 12. So again, if you think back to our scales, when we were doing measurements, that was going to be 10 to the negative 3 for a milligram. This is going to be 9 more zeros before we actually get to measuring the length. So we measured in millimeters, also the negative 3. Again, 9 more zeros in front of those numbers. So it's really, really small. The hydrogen atom is about 32 picometers in a radius. Right now, remember, the nucleus is a dense positive center. So the nucleus is even way more smaller than that. So it's, again, we saw the masses. Now we're looking at distances, and you're going to go down another 3 powers or so, down to negative 15 picometers, roughly. If the atom was the size of a stadium, so if we think about a sports stadium, the nucleus would be the size of a marble, just to give you some sort of idea. So again, the radius of the nucleus is somewhere around 10 to the negative 15 meters. Now, when we think about density, that means the density of the nucleus, because it's so small and all the mass is there, will go upwards of 10 to the 14th in grams per centimeter. Now, again, this isn't necessarily stuff that you'll need for an exam. This is sort of just to get your heads wrapped around how small we're talking. Right? Now, what do you need to know for the exam? Well, you're going to need to be able to count pieces. So we need to know that the atomic number is equal to the number of protons. We need to know that the number of protons determines the kind of atom that we're dealing with. We need to know that the same number of electrons in the neutral atom. So our protons and our neutrons are equal to one another as long as it's a neutral atom. There's also the mass number. The mass number is equal to the protons plus the neutrons. And that means that we have all the things that have mass will be accounted for. Now, again, when we look at the periodic table, there's mass numbers on the periodic table. You'll notice those are decimal points. For right now, I want you to ignore the decimal points, right? Because if I take two whole numbers and I add them together, I do not get a decimal point. I get another whole number. And so when we're dealing with mass numbers on our first assessments, it's always going to be a whole number. You're going to be calculating those based on the atomic number and the mass number. Okay, so don't fall into the trap of using your periodic table for that mass number just yet. Now we will be eventually using that mass number, but next we're going to explain what the difference is in the mass number with the decimal point and why I'm telling you now that your final answers need to be a calculated answer for the first assessments. And that's going to be isotopes. Now if you think back to Dalton, and I said, number 1 was good, number 2 was good, but number 3 wasn't, and we put a little mark on it, and the number 4 was fine. The one that was wrong was the one where he said all atoms of carbon would be exactly the same, and all atoms of oxygen would be completely the same, but carbon doesn't look like oxygen. So it's partially true. Carbon and oxygen look completely different. But where he was wrong was atoms of the same element can actually have different numbers of neutrons. Now that doesn't affect anything else, right? Because neutrons are neutral. However, what it does affect is that mass number. So we could have the same carbons with different mass numbers. Chemically, they're going to react exactly the same for the most part. I mean, mass does play some part, obviously, in speed, but percentage-wise, you wouldn't see a difference at all. So that means that when we have different mass numbers, we have the same atom, but we still have two different things, and we call those isotopes. So how do we deal with isotopes? Well, we name them. We name them out separately. And the way we do that is we take the mass number and simply hyphenate it after the name of the element. So for instance, I'm saying there's different carbons. Well, that means we could be dealing with carbon 12, which is the normal carbon, or we could be dealing with carbon 14. Right? So hopefully that makes sense. Now, what's the difference between those two? Well, carbon 12 and carbon 14 have the same atomic number because they're both carbon. That means they both have an atomic number of 6. However, if I take the number of protons plus the number of neutrons, that's going to equal the mass number. So we can see in carbon 12 then, we're going to have 6 neutrons, whereas in carbon 14, we're going to have 8 neutrons. Same thing for uranium. So uranium-235 is going to be one specific isotope of uranium. Now there are several different types of uranium. Some are positive and some are negative in the mind's eye, right, society. Right? One is used for nuclear weapons, the other one's used as a fuel. So one would be potentially good and the other one we look at as potentially bad. The isotope is going to matter. And we'll talk more about isotopes in Chem 110, but in Chem 100, I just need you to know the names of these guys right now. We're not going to worry about the different isotopes as far as how they're going to react in the nuclear sense. But in 110, we'll look at how the nuclear piece can impact that, and so the different reactions they'll undergo because of the isotope number. Now, how do we keep track of all of this? Well, right now I'm going to introduce you to atomic mass units, AMUs. And the way we come up with this is 1/12 of the mass of a carbon-12 atom. All right, so the numbers are kind of, I don't want to say they're made up, but the scale is a man-made scale, okay, for AMUs. And I don't want to spend a lot of time on AMUs simply because when we get another chapter or so in, we're going to be talking about the mole. And when we introduce you to the mole, I'm going to have a whole different unit type for the periodic table, right? So for right now, they're AMUs, atomic mass units. Each isotope has its own atomic mass, and what we're going to do is take the average from the percent abundance. So basically, we're going to just calculate averages. Now, a question with AMUs would look something like this. Calculate the atomic mass of copper if copper has 2 isotopes. 69.1% has a mass of 62.93 AMUs, and the rest has a mass of 64.93 AMUs. So what we're going to do here is calculate what the mass of the copper should be. And then what we're going to do that is by the percent abundance. So the percentage here is giving us the percent abundance. Now we know all of the coppers have to equal 100%. And it tells us the rest has a mass of this mass over here, 64.93. So 69.1% has this mass, the rest of it has that mass. So the first thing we do is figure out what's the rest. So I'm going to take 100%. And I'm going to subtract that 69.1. Remember, this is a percentage, so it has to equal 100%. So that's going to be a 9 there, and that's going to be a 0, and of course a 3. So the rest of it then is 30.9%. Now, if you recall from your algebra courses and your math courses, if I want to do percent abundance, what I'm going to be doing is taking this percentage and getting rid of the percent. And then I'm going to turn that into a decimal. So it's a percent to a decimal. And the way we're going to do that is simply divide by 100. So we're going to move this over 1, 2. And so 0.691 is now the decimal format of that percentage. And I'm going to multiply that by the mass that actually is this percentage, which is the 62.93. And then I'm going to take the rest. I'm also going to convert that. So we're going to divide that by 100. And that's going to give me 0.309. And I'm going to multiply that by the other mass, which is the 64.93. All right, now I'm just going to carry those out. So I'm going to get my handy dandy calculator out. Let's see, calculator, and we're going to do 0.691 times 62.93, and that's going to give me 43. How many sig figs do I get here? Well, I have 3 in my percentage and 4 in my mass, so I'm going to keep 3 of these. So 43.5. Now I'm going to do the same thing with the 0.309. So 0.309 times 64.93. Keep hitting the wrong buttons here. 0.309 times 64.93. And I'm going to get 20.1. And so when I add these up, I get a 6, I get a 3, 6. And this, of course, would be AMUs, would be the unit we're using right now. And so if I go to my handy dandy periodic table now we can compare our 63.6 to the actual mass of copper. And on here I have 63.55. And this was from the periodic table, PT. Okay. And so as you can see, we came pretty close to that with our sig figs, right? I mean, we have 0.6, that's what this would round up to. So if I could have carried out a fourth sig fig, maybe we would have gotten something a little bit closer, right? But of course, our percentages dictated that we had to have 3 sig figs, and when we did that, we still got in the ballpark. We would consider this really good. We nailed it. And of course we should, because all the percent abundancies and all the AMUs are what's going to give us that decimal point that we see on the periodic table. So, to prove that, what I'm going to ask you to do is try another problem. Magnesium has 3 isotopes, 78.99% magnesium 24 with a mass of 23.9850, 10% magnesium with 25 with a mass of 24.9858, and the rest is magnesium 26 with a mass of 25.9826. What is the atomic mass of magnesium? So again, we'll take each one of those percentages, we'll turn them into decimals, and then multiply them by the AMU value. Then sum up those 3 numbers. That answer, according to the periodic table, let's see, we're doing magnesium, which is number 12. That mass should be 24.31 AMUs. So I'm going to have you go ahead and work that problem out. You can submit it to me for bonus points, and hopefully you'll come out to 24.31, and that way you'll know that you've got the bonus points. So I'll be looking forward to emails for that one, and then I'll be putting that into the score manually. All right. If you have any questions about how to calculate these AMUs, make sure you get in touch with me or check with the tutor. But that's it for those. I'm not going to spend a whole lot of time on those. We've done 2 problems and you've got 1 for extra. So just to reiterate again, remember the atomic mass is not a whole number because it's going to be that average. So when you're looking at the periodic table, what you're going to have to do is differentiate between the question types. Right now, the only question types I'm going to be asking would be ones where you're calculating the number of neutrons or you're calculating the mass. And so you're going to have a whole number value, not the average that we're seeing on the periodic table. Moving forward, we're going to be doing measurements with those masses, which means you're going to have a mixture of the 2 isotopes or 3 isotopes or 5 isotopes, however many are there. You don't need to know how many isotopes each atom has. You do not need to know the masses of the different isotopes. I will provide that information for you. I will ask you to calculate the number you see on the periodic table. Now, if I'm asking you to calculate it, much like that last slide, I'm going to expect to see your work. Okay, so if you just turn in a piece of paper or send me an email, excuse me, with the number 24.31 AMUs on it, I'm not going to give you any credit for that. I'm going to want to see the math. I want to see how you did the problem to make sure you're doing the percent abundancy as a decimal times the AMUs and then summing them up the correct way. Okay? Now, the decimal numbers on the periodic table are those average masses. Okay, that's where that's all coming from. So again, just to reiterate, what do you need to pull out of these units? Protons equal the atomic number. And if you're feeling like this is redundant, it's because it is. This is like the 4th time you're going to see these slides in here because it's important. You have to get these pieces down in order to move forward. Atomic mass is equal to your protons plus your neutrons. Your protons, with the exception of nuclear chemistry, will never change. So carbon will always be carbon unless it's a nuclear change. So basic chem, you're never going to see that. We're not going to look at nuclear at all. Chem 110, towards the end of the semester, we'll do a chapter on nuclear chem, and you'll see it there. Okay? But other than that, protons never change. Change in neutrons means a change in the atomic mass. We call those isotopes. Okay? So almost by definition, that's an isotope right there. The change in neutrons means the change in atomic mass. And now we haven't talked about this yet, but it's coming soon. A change in electrons will mean a change in electric charge. Okay, a change in the number of electrons means a change in the electric charge. All right, so we're going to stop here. That's our basic principles of our atom. And next we're going to get into Bohr's model. And so we're going to come up to what do chemists use now and what are some differences. And notice the other thing we haven't talked about in any detail yet are those little electrons. And so we're stopping here where we're saying, okay, electrons equals protons. But now let's talk about what we're going to do with those electrons and how we keep track of them. So that'll be in our next segment. All right, talk to you soon.